Dr. Sheng is from Stanford University. His research focuses on wearable and flexible ultrasound technologies for continuous, non-invasive physiological monitoring. And our next Q&A session will be at 9:20 as well. Thank you for joining.
Yeah, so good morning, everybody. Thank you so much, Dr. Pirahanchi, for this wonderful opportunity for me to present our work here. So, as Dr. Pirahanchi mentioned, I'm from Stanford University, and I work on those wearable ultrasound patch for cerebral blood flow monitoring. Cerebral blood flow is actually a strong biomarker for many diseases, such as hemorrhage, atherosclerosis, emboli blockage, so on and so forth. And here are some of the statistics showing the significance of those type of diseases. And how to diagnose, right? So there are tools to do it very well. One is called the transcranial Doppler (TCD), and I don't have to preach to the choir, how useful this tool is. And you can measure those, flow velocity, peak systolic and diastolic. And you can provide real-time monitoring. It's non-invasive. It's highly portable. And it's also very safe, right? So it's non-ionizing radiation. So lots of advantages. But there are two, I would say, significant limitations with the conventional transcranial Doppler device. First is that it's highly uncomfortable. Because this probe is pretty rigid, you will need a very, very, I would say, tight, uncomfortable fixation mechanism to keep the position and the angle of the probe on the human brain, on the scalp. And because of that, it leaves lots of irritation and redness. And because of that, you can only do this monitoring for short periods of time, typically for half an hour. And the second challenge is that this technique is highly operator dependent, which means you need lots of training and skill sets to do this, accurately, quickly, efficiently. And if there are any motion or those misalignment, your results will be significantly distorted. This is very, very challenging. So to overcome those limitations, we demonstrated a flexible wearable ultrasound patch like this. So this patch can be placed on any part of the human brain. We selected this temporal window because it's already relatively thin, very flat, and therefore the attenuation, the aberration is relatively small. And those are the structure exploitative view of the patch. We use a piezoelectric transducer for transmit and receive ultrasound. And those are the multi-layered electrodes to control each one of the elements individually. And at the bottom here are those flexible stretchable ultrasound patches we fabricated. They are 16 by 16, 256 elements, and these flexible, very low profile, and they can be conformally wear on the human scalp. And here are the parameters we used. We used low frequency 2 megahertz because low frequency has relatively low attenuation aberration through the temporal window. So the first question we have to address is the device safe or not for continuous monitoring, right? So we put this patch on the human scalp for continuously working for 4 hours. And as you can see here, the temperature on the scalp actually becomes stabilized. It does not, increase anymore because of this, temperature exchange with the, environment and also with the human skin. It stabilizes at 32.5 Celsius. And that is completely compatible and comfortable, for the human body to wear for long periods of time. And we have also done those, intensity measurements through the human bone, right? We used a, human skull. So this is a real human, bone. And we put this patch in the water and measured the intensity inside after penetrating, the scalp, the bone, right? So you can see that those intensities are measured here when the intensity is focused and diverged. The intensities are, this spatial peak temporal average intensity are all well below this 720 that is regulated by FDA. So that means even inside of the skull, after penetrating the bone, the intensity we use is, very, very safe. So we use those two modalities. One is focused for recording the flow velocity, the spectrum, and diverged, this beam to map to do 3D those imaging, this power Doppler imaging of the cerebral vessels. So how do we enhance the signal to noise ratio? After this ultrasound has been attenuated by this bone, right? So we stand on the shoulders of giants by learning from the literature. So we use a technique called ultrafast imaging. If you do not know what it is, it's basically a technique that allows you to transmit and receive hundreds of thousands of ultrasound pulses every second so that you can receive lots of data and you can do those averaging and do those power this filtering, and eventually the signal to noise ratio is significantly enhanced. So those are the power Doppler imaging of the vessel, the cerebral vessels we could get. It's 3D imaging, and we can identify all those major branches from the this is so-called circle villus. And for a typical human subject, a healthy human subject, the circle villus is pretty symmetric. Left side and right side, have pretty uniform flow distribution. So, there are like quite a few windows we can leverage besides temporal window, such as this orbital, submandibular, and suboccipital windows that we can record different parts of those, cerebral vessels. And this patch is connected to a flexible cable. This cable provides, those electricity and data, right? And eventually fed into a desktop system that can do this data processing and displaying the image. So those are the results. You can see that these are schematics, but from those schematics we can get those a flow spectrum from various parts of those major branches, as you can see here. Anterior cerebral, occipital, middle cerebral, so on and so forth. And we have compared our measurement results from the wearable patch to a clinical transcranial Doppler operated by a over 30-year experience, clinician. And as you can see here, we validated on 36 participants. And from the Brand Allman analysis, you can see the results are very correlated, and they have very, very small discrepancy between those two measurement modalities. We have done analysis for the peak systolic and the diastolic and the mean flow velocities. They all have very, very high accuracy. So we did some like maneuvering control experiments. As you can see here, when we put this patch on the temporal window, and the subject was doing those different type of exercise or those maneuvering, right? Such as this hand grip. You can see that when this person was like doing this hand gesture, and this middle cerebral artery mean flow velocity will actually pretty change pretty significantly, right? And when he was doing this, while Sawa maneuvering, you can see that which is basically in holding and breathing the air. You can see there's some middle cerebral artery flow changes. All those changes match our expectation that we learned from the textbook. And we have done more like that, such as generating the words by speaking, so on and so forth. And those are the different periods of phases, and visual stimulation. We also expect similar things from happening. And the most interesting thing is that when we were like pressing on this left common carotid artery, and that's where the flow from the heart, right? That's where the flow into the brain is. That's the source, one of the sources. You can see that under normal condition, the flow to the left side and the right side are symmetric, as indicated by the uniform width of these arrows. But when we compress on the left side, the flow to the left side of the cerebral artery is reduced, as indicated by these thinner arrows. And automatically, you don't have to do anything. This is after like millions of years of evolution, the human body automatically adjusted the flow to the right side. The flow is thicker, and on the back side, this is so-called this autonomic compensation, right? So this is not very surprising. But what is surprising is that when we were doing this 4-hour-long middle cerebral artery monitoring, and in the middle of this monitoring, the subject becomes sleepy and drowsy. You can see that we observed this peak systolic velocity of the MCA flow become like oscillating, right, at the frequency of around zero point 0.1 hertz. This oscillation is so-called B wave, and it reflects those neuromuscular coupling. It's a evidence for those lymphatic fluid flow, memory consolidation, removing all those metabolic waste, so on and so forth. That means our technology can provide a strong evidence for lots of fundamental neuroscience research. So that is for this, cerebral vessel monitoring, right? Actually, this technology is a platform. We can use it for, monitoring all kinds of vessels, deep tissues in the human body. And recently, we, published a comprehensive review article trying to summarize the status of the field. So my group mostly focus on those monitoring imaging of various kinds of organs and, tissues. People in the field have also used ultrasound for stimulation, for activating, suppressing neural activities and pain, or delivering drugs. People also try to use ultrasound for delivering energy wirelessly to those implants, right? So you can expect the expanded battery life. You can also code ultrasound those frequency and phase for data transmission as well. So with that, I want to acknowledge my group of students and postdocs. I'm learning from them every day, and also my critical collaborators and also funding agency. The size of the logo is roughly proportional to the amount of funding I receive, I accumulated over the years. Thank you so much for your attention.